Okay. So this one says the 10 kilogram wheel has a radius of gyration 200 millimeters. The wheel is subjected to a moment of 5t, which is important because this is actually given to us in terms of time. We're going to need to do calculus. T is in terms of seconds, determine its angular velocity when time is 3 seconds, starting from rest. View the reactions when the fixed pin A exerts on the wheel during this motion. So we got to find two things. One, we got to find the velocity when t equals 3 seconds, and then we have to compute the reactions. All right, so look at what they gave you. So we're at the point where you got to know what to do. They're not going to tell you what to do. They also gave you the radius of gyration, which is important. I actually need to go look up that equation because I forgot if it's squared or not, but that's okay. So look at what they gave you. They gave you mass. Right? They gave you mass. They gave you time. Oh, they gave you moment, which is an example of force. So they gave you moment, which is like force. Okay. And they gave you time. And they want you to solve for W, which is like solving for V. And so if you remember what I told you about there are only three aspects of kinetics, excuse me. There's only three aspects. So aspect one will be acceleration, which is free body diagrams, right? Yeah. Acceleration uses mass, force, and acceleration. Two is work energy. Work energy uses mass, force, velocity, and distance. Well, I'll put a delta S and change of position. All right. And so generally they'll ask you to solve for velocity, change of position, or force. But at the end of the day, those are your four variables that are generally included. And then lastly is impulse momentum. And impulse momentum uses mass, force, and velocity, just like work energy, except it uses time instead of distance. And so if you think about that, denote the variables with kinematics. Kinematics variables are change in position, velocity, acceleration, and time. And so look at each one. It's really, really convenient. Each one of these gives you a certain thing. So acceleration goes to your body diagrams. The velocity and change in position go to the work energy, and your velocity and time go to impulse momentum. And so all four kinematics variables end up being used in their own way when it comes down to looking at how the forces affect them. And so as long as you know what they're kind of gave you and what they're asking you for, you automatically, if you remember this, you will automatically know what to do. So taking a look at what they gave me, the moment I saw that they asked me for time, the moment I saw that they gave me time, I automatically started thinking I was going to use impulse momentum. When they asked me for the velocity, that kind of fixed itself in my head automatically because they gave me time and all that stuff. Mass and moment are just examples of, mass and moment are just examples of mass and force. Moment is just rotational force. And so automatically I know I'm going to use impulse momentum. Make some sense?
Yeah.
So we're going to use impulse momentum. And we're going to ride out with that. So when it comes down to when it comes down to rigid bodies, yes, generally you create three equations. You got to create an equation in the X. You got it. Oh, I'm putting red. You got to put an equation in the X. You got to put an equation in the Y, and you got to put an equation in the Z. But when you draft these equations, you have to draft them with respect to how impulse momentum is done. And so,
yeah, I thought Z would just be moment.
Yes, that's a moment. Yeah, that's exactly right. The moment is in the Z direction. Whenever you have that rotation, that will represent going into or out of the page, which is the Z direction. So I just call it the Z direction because sometimes I
This
forget to
makes
say the
sense.
rotation.
Okay.
So generally, it's the z direction equation that gives people the most heartache. So let's just go through the x and y like we normally know how to do. Impulse momentum equation is sum of all moments. I'm sorry, not sum of moments. The sum of all momentums plus the sum of all impulses. This is initial momentums equals the sum of all final momentums. So impulse equals the change in momentum. Well, we know impulse is the integral of force with respect to time, or if you put it in simple terms, force times change in time if the force is constant.
Mm-hmm.
Okay. So we have that. Now, if you look at the information that's given to you, I'll put it in orange because I don't want to use too much red. None of this information that was given to you was linear. All of this is rotational, all rotation information. Since it's all rotation data, I'm just not going to even consider. I'm not going to consider the X and Y axis right now. I'm just going to go straight to the Z axis because that's where all my data was given to me. Make some sense?
Yep.
All right. So what we're going to do is we're going to apply the impulse momentum equation to rotation. So impulse momentum, this is the linear form. All of this data is linear. And now, obviously, we have to do a rotational version. A rotational version is the same exact thing. Remember, all the linear terms have their angular counterparts. So linear momentum P is written as angular momentum L, if I'm not mistaken. I always forget if it's L or H. Some people use different ones. I think it's H. Actually, in the last book that I saw was H. It doesn't really matter. You just got to know which one is which. Well, we're going to use H. Okay, I forgot that this is actually a vector equation. H plus the sum of all angular impulses, okay, equals the sum of all angular momentums. So it's the same thing, except every term is now called the angular version. So angular momentum, angular impulse. And you got to know that angular impulse equals, it's the integral, and instead of saying force dt, it's going to be moment dt. Makes some sense? Because the counterpart to force in rotation is moment, which when you simplify it becomes moment times change in time. That's if the moment is constant. In this case, it's not. This is the rotational version. Are you following me so far?
Mm-hmm.
We're at the point where the only thing that exists that make the problems hard now is the existence of the z equation and knowing how to use it, how to write all of your angular terms and convert from angular to linear. If you can do that, everything is the exact same. Okay. You also have to know, of course, that I didn't write it, but you have to know that regular momentum is equal to mass times velocity, and angular momentum is equal to not mass times angular velocity, but the moment of inertia, I. Is that really what we use, I? Wow.
Mm-hmm.
I forgot that they use eyes. And I'm only realizing just now that this has two eyes. That's really annoying. All right.
Yeah,
So
it did confuse me when she went over it in class a little bit about the two eyes, but I just left it alone.
I never realized that until just now that they're both I. Like I know the equations not by their letters, but by the ideas. So when I read this, I know what they mean, but I've never recognized at once that these are actually that they're both I. Funny enough, whatever. But as I, mass becomes I, which is honestly probably the most convenient thing in dynamics, I will admit. The moment of inertia to me is the most confusing thing in dynamics, mathematically, but it is the most convenient concept that I saw in that whole class. Because what it does is when you create the rotational version of mass, then it becomes a simple equation IW. Now what happens is when you learn it in particle form, you got to do mass. How did they do it? It was using the right hand rule. Give me a second to think about it. Using the right hand rule would have been the arm cross the momentum. Arm cross momentum is a really funky way of explaining it, but when you bring it into rigid body form, the presence of the I, like the fact that that comes into being, instead of using R cross P for every single part of the body, you can create IW. Man, that makes it so much cleaner. It's like the most genius invention of dynamics. But yeah, so we're gonna use. I always say this: we use the rigid body IW, rigid body. And for this, we use it on particles. And that's the same thing for when it comes down to doing force, because moment is technically written as R cross force, but we use I times alpha when we're doing rigid bodies, which is really, really convenient. You follow me?
Mm-hmm.
But what happens is in this problem, we have a wheel, and this wheel is unbalanced, right? This wheel has some mass on the outside, some mass on the inside, some mass like that. That's where the mass is. So there are huge void spaces where there isn't mass. I'm not gonna go and find a fourth of a disk and cut them out. Instead of doing that, we use what's called the radius of gyration, this guy right here, to solve for the I in a different way. And I don't remember the actual equation. Do you happen to remember it? It's like I equals mass squared, I think, but I got a quote. I don't want to mess it up, so I'm going to look it up on the internet real quick.
That's the first time I've ever seen a radius of gyration.
Really?
She were in class. That's why I picked that question.
So now we're learning
moment of inertia. So,
all right, that's not a problem at all. Let's do it. I'm just gonna go on Wikipedia real quick and get the equation because I don't want to mess you up. It's why did I go to Wikipedia? Wikipedia always gives you too much. Let me go back to something that's a little bit simpler. Mass times k squared. So I was right. All right, dope. So radius of gyration. When they give you the radius of gyration, you have to just know I equals mass times k squared. So when they give you the radius of gyration, I actually prefer that they give you the radius of gyration because it's easy. Instead of you having to go and like look up a moment of inertia or like build a moment of inertia based on the shapes. I love it when they give radius of gyration because it's just mk squared. Make some sense?
mm-hmm.
So now that we have all of our pieces, we're just gonna plug and chug. We're gonna assume that this direction is the positive direction, and we're gonna say, okay, in the beginning it started from rest, right?
Yep. So that means the initial is 0.
Exactly. So this guy nulls out to 0. We're going to add the summation of the angular momentums. Angular impulses. The angular impulse is given explicitly by this, where I say the wheel is subjected to a moment. Of course, if there were extra forces on it, like let's say let's put it in purple. Let's say they drew a force right here, and they drew a force right there, and they drew a force like right there. You would have to then use the arm attached to those forces. You see what I'm saying?
Yeah, and
find extra. Yeah, to find extra values of the thing, because that's the problem with moment. Moment can be caused by what we call a couple moment, which is what they put on the problem in the first place. A little rotational arrow is called a couple moment, or it can be caused by forces acting along a distance, and that actually gets a lot of students. So when you're looking for moment, you have to make sure that you can consider all of your linear forces, and if they cause rotation, and any couple moments that are just drawn on that represent the fact that somebody's twisting that shaft, like from an engine.
Yeah.
Okay.
Yeah.
Dope. So in this problem, we only have the couple moment, which is nice. And so we just got to take the integral of 5t dt, because that's what they gave us. They gave us a function, so we got to use the calculus. If it was just 5, we just use 5 times 3. But because they gave us a calculus, we're going to use 5 times 5t dt and integrate it for 3 seconds. And that's got to equal my new angular velocity. Make some sense? Which is equal to I times w, where we know I is mass times k squared times w. Cool?
Yeah.
And we know mass is 3. We know mass is 10. We know k is 200. Well, actually, it's 0.2 because it's millimeters. So all we have to do is solve this bad boy for w. So we'll just bring it on down. We're going to get 5t is going to give me 5t squared over 2 from 0 to 3, which is going to be 5 times 9 over 2. That's going to equal 10 times 0.2 squared times w. And automatically, with that being said, I can automatically solve for w. You following me?
Mm-hmm. Yep.
Solve for w. W2, which is the final angular velocity, is just going to be divided by that. It's going to be 2, so it's going to be 9 over 4. And 9 over 4 times 0.04, whatever that is. So 9 over 0.16. I don't know what number that is, but that's the number that we're going to get. That's going to be in radians per second. You follow me?
All right. Yep. So